Hi, welcome to another session with Mrs. John. Today we are going to look at torque and acceleration, and this is mostly a problem solving lesson, but in order to understand why we are doing this and why the problems involve things like wheel and axle, I'm just going to give you a little bit of background information. So if you look at the world around us, there's all sorts of complex structures, machines, things, even a little thing like a car, like a toy car here, is made of lots and lots of little parts. But actually, if you analyze them, all these little parts actually boil down to four simple machines. And these four machines are what makes up all the other bigger things that surround us. So one of them is the lever. Okay, so you got your hinge moving things, and then you've got the gear, which I'll show you on a guitar. So if you look at the back of this, there's these little, I don't know if you can make out, there's these little wheels with grooves, interlocking ones. So when you turn these things, it's these grooves that move against each other. So you've got that, you've got and then the other thing is the wheel and axle and the pulley. So what is a wheel and axle? It's kind of like a doorknob. So, which is the wheel and axle, which is a machine, is a little different from the wheel and axle of a car. So the car's got the wheels and it's got the axle lies between the wheels. And what the axle does in the car is kind of bears the load of the car. But the wheel and axle we are talking about is quite different. So the wheel and axle, it's actually two cylinders which are fused together, so they move as one. So the bigger one is called the wheel, you can turn, and the little one is the axle. So notice when I turn the wheel, the axle turns with it as well. So they move together as one. So how is this important, and why we're looking at the wheel and axle is that if you wrap a string around either the wheel or the axle, and at the end of the string, if you have a load or a mass, and if you let it go, the mass is going to fall down. It's going to accelerate because of gravity. And so why is that? What has that got to do with what we are learning today? Is the mass which is tied to the rope is accelerating, and that force, the unbalanced force, causes acceleration, but it also results in a torque, the turning effect. And actually, if you know what the linear acceleration is, how quickly is it falling down in a straight line, and the mass itself, it's possible to calculate the size of the torque, and it's also possible to calculate the tension force. Okay, if you know what's the unbalanced force, and if you know these two, and if you also know the radius of, if it's the wheel, you use the radius of the wheel if the rope is wrapped around the wheel, and you use the radius of the axle if the rope is wrapped around the axle. Okay, so if you know that, you can also calculate rotational inertia. So this sort of thing is useful for calculating two things. You can get the torque, or as well as find out what's the rotational inertia of something. Okay, so the sort of questions that we are looking at today start with simple. So this is just a wheel with a rope wrapped around it. And so radius is the distance from the center, and the rope is along the periphery. So that's a radius. And there's a mass. And if you let go, the mass is going to accelerate down. So that's what happens. Okay, so it falls down. Now, in order to analyze this further, we're going to look at the forces that are acting on this whole system. So this is the wheel that's spinning or rotating. And because there's tension force, now tension force acts both ways. So it pulls this wheel down. So the force acting on the wheel is just the tension force. But however, if you look at the forces acting on the mass that's accelerating down, there's two forces. So there's the tension force holding the mass up, but there's also the larger gravity force pulling it down. Now these two forces are unbalanced. That's why it's accelerating. And because it's accelerating downwards, the force downwards on this mass has to be bigger than the force upwards. Okay, so I've just got in this one just the forces acting on the mass. So the force downwards is bigger than the force upwards. And the difference between these two forces gives us the unbalanced force. And we know from earlier that this unbalanced force is equal to ma. So with this much in mind, let's look at solving the first question in the booklet under torque and acceleration. Okay, so I'm just going to do the first question, which is this question. So this question has got a wheel, that's a bigger one, and the axle's the smaller one. And in this particular case, the rope is wrapped around the axle, so we've got to take the radius of the axle into consideration rather than the radius of the wheel. Okay? So I've just got it down on this. Okay, so here is question 1. So I've just got some numbers here. So the radius of the axle is 0.20 meters, and there's your wheel and axle. So wheel's a larger one, the axle is a little one, but when the mass is falling, the whole thing rotates. They don't rotate separately or independently of each other. The whole thing is spinning together. Okay, so they have a common angular velocity. So this is the acceleration, 4.1 meters per second squared. The mass itself is 3 kilograms. So in order to calculate what is the unbalanced force, we just use F equals ma. There's your m, there's your a, and you get the unbalanced force. And we also know that this unbalanced force is a difference between these two forces, gravity force and tension force. And so it's possible to get tension force by subtracting these two. And then I just got the numbers. So mg is 3 times 9.8 minus ma, it's still 3, and acceleration is 4.1. It's got a little rubbed off. And so tension force, the difference between the two, it works out to 17.13 newtons. Now, if we needed to calculate the torque is tension force times the radius, and we know from the top the radius is this value. So you just multiply those two, and it's possible to calculate torque. If we needed to go one step further and you wanted to know what's angular acceleration, if you know linear acceleration and radius, it's possible to put these two together and get angular acceleration. And one more step, which is not in this question, you know torque is I times alpha. So you know the value for torque, which you just calculated here. And you also know the value for alpha, which is angular acceleration, by using linear acceleration and radius. Then there's only one unknown, which is the rotational inertia. And that's how you solve the other problems. So what I'll do is I'll work out the answers to the questions for you to check. And I think Mr. Wong's actually talked his class through one of the later questions, and we'll upload that video as well. So hope you understood this lesson. This is on torque and angular acceleration and how we calculate any of these, including calculating rotational inertia. So bye for now and enjoy the rest of your day.